Big O notation answers one question. When the input gets large, how fast does this thing grow? Not how fast it runs on your laptop today, not exact numbers, just growth in the long run. Suppose you have two programs. One works a bit slower as the input grows. The other explodes in time as the input grows. Exact timings depend on hardware, language, and constants, so comparing raw seconds is pointless. What matters is how the work scales. Big O is the tool for that. At its core, Big O compares two functions by growth rate. When we write f of n equals big O of g of n, we are saying this. Eventually, for large enough n, f does not grow faster than a constant multiple of g. Past some point, f stays under a stretched version of g. Two ideas are doing all the work here. First, eventually means we ignore small inputs. Second, constant multiple means we are allowed to scale g up. Because of that, constants and smaller terms stop mattering. Now the notation. F of n equals O of g of n. Read that as f grows no faster than g up to a constant for large n. That is an upper bound on growth. Here is the formal version, and this is the precise meaning. There exist constants c greater than 0 and n, such that for all n greater than or equal to n, the absolute value of f of n is less than or equal to c times the absolute value of g of n. C is the scaling factor, n is the cutoff point. Absolute values just keep the definition clean. An example makes this concrete. Take f of n equals 3n squared plus 2n plus 7. We claim this is O of n squared. For n at least 1, 2n is at most 2n squared, and 7 is at most 7n squared, so the whole expression is at most 12n squared. That gives us explicit constants. We are not finding the best constants, any ones that work are enough. This shows why lower order terms disappear. As n grows, n squared dominates n, and n dominates constants. Big O keeps the dominant shape of growth. This is why Big O is everywhere in computer science. If T of n models running time, then O of n means work grows roughly in proportion to input size. O of n squared means doubling the input roughly quadruples the work. O of log n grows very slowly. This lets us compare algorithms without caring about machines or implementations. There are common growth classes you should recognize. Constant time means the work does not grow at all. Logarithmic time grows extremely slowly, like binary search. Linear time scans once. And log n shows up in efficient sorting. Quadratic time comes from simple nested loops. Exponential and factorial growth explode and become unusable fast. Big O is not alone. Big omega is a lower bound. Big theta is a tight bound, meaning same growth from above and below. Little o means strictly smaller order. Big O by itself is not necessarily exact. People often say O of n when they really mean theta of n. This leads to common mistakes. Big O is not an equality. Saying something is O of n does not mean it is not also O of n squared. Big O does not give exact running time, and Big O does not automatically mean worst case unless you say so. One last thing. Big O is about what happens eventually. For small inputs, constants can dominate and flip which algorithm is faster. That is not a contradiction. Big O is a long-run comparison tool. So the takeaway is simple. Big O describes growth, not exact values. It ignores constants and small terms. It focuses on what dominates as inputs get large, and it gives us a clean language for reasoning about scale.